Hello, everybody. We're very pleased today to have Eleanor Knox from King's College London, and she's going to be talking about constraints and spatiotemporal explanation.
All right, brilliant. Thank you very much for organising this to Alan and everyone else. I'm hugely interested in this topic, but I maybe should give some context. So Al looked at my slides and said this looks like Mark Lang's talk. There's a bit of truth in that, this is really work I did writing a review of Mark Lang's book. And I've left pictures of the book up all over the place because, in part because I think it's a wonderful book and everyone should read it, and in part because I think that claiming a lot of this material for myself rather than being slightly more in the position of reviewer and pointing out how diverse and interesting the applications of Lang's work are would be inappropriate. Yes, that's proviso number one, is that in a sense this is review work rather than my own, perhaps apology, etc. Number two is in advance, is that there are two loud small children in my house, and when I laid out my house I didn't think very hard about working at home with two small children, so they're bound to come past my office at some point. Apologies for the interruption if you hear screaming in the background at some stage. All right. Okay, so what do I want to do today? I want to look at one quite particular application of explanation by constraint to space-time physics. I think it's really interesting because I think that explanation by constraint as developed by Mark Lang wasn't particularly developed for this purpose, and it turns out to have a really interesting application to a particular debate in the philosophy of space-time physics. So I'll explain how that works, and then I'll say something about how the metaphysics that underpins Lang's conception of explanation by constraint. It's a pretty heavy and a pretty substantive metaphysics that we might not all want to buy. So the question I'll ask at the end, which I don't have a kind of adequate answer for, is whether we can help ourselves to something like Lang's explanation by constraint without adopting the full picture of modal metaphysics that he has. I'm hoping maybe some people here might help me think through that. So you can challenge me on it in the questions and I'll try and think on my feet. Good. So what is explanation by constraint? Well, it's supposed to be a kind of non-causal explanation. This is explanation by constraint a la Lang. This is the version I'm describing. And the kind of classic examples of non-causal explanations are, of course, mathematical ones, and they're the unproblematic versions of this particular view, right? So classic philosophy of maths example, why can't we divide 23 strawberries evenly amongst 3 children without cutting them? And if you want to explain that, you're going to appeal to a mathematical fact. And that modally constrains a given physical situation, says Lang. So we're puzzled about mathematical explanation. He says, look, it's a version of a modal constraint. You'll never succeed in your strawberry portioning because of the fact that 23 is not divisible by 3. And that makes that impossible. And you can pick almost any of the examples from the very large literature on explanation in mathematics and explanation of physical phenomena by mathematical facts. And this kind of model will probably fit them fairly well. I mean, the moment you have a mathematical fact, it arguably would function fairly decently as a modal constraint. It's impossible to contravene the laws of mathematics. But what about outside of mathematics? So to some extent, what Lang is doing is taking a kind of a discussion that doesn't focus on constraint in philosophy of maths, moving it away from this kind of question about Platonism and applying it much more widely to non-causal explanations. But we can apply it also on the same kind of model to laws of nature. So some laws of nature involve the details of dynamics, right? But there are a lot of laws of nature, things that physicists talk about, that invoke general principles. I mean, Lang's example is the conservation of energy. I actually think that's always a bit of a sort of funny one. I think it's sort of less used in physics than perhaps people think it is. But certainly conservation principles are an enormously important category in physics. And you might think that general principles that you invoke might either be constraints or coincidences, right? In much the same way that you might think that laws of nature themselves might either be law-like or coincidental. If they're really, there's a question about whether something's an accidental generalization or a law. Lang thinks there's a similar kind of thing going on when you talk about the kind of law of nature that functions as a principle. It could be a coincidence that all of the laws of nature have some symmetry property, or it could be a matter of constraint. So if a law of conservation is a coincidence, then it merely states a fact about the symmetry properties of the dynamical laws. It says nothing about the modal situation. So it says nothing about the possibilities for alternative or new dynamical laws. But if it's a constraint, then there is some sense, and of course we need to be careful about what sense this is, in which the various dynamical laws must possess the symmetries that make energy a conserved quantity. If there are other dynamical laws, then they too would respect the conservation of energy in some appropriately restricted modal domain. So part of this picture is going to be that we actually have a nested modal hierarchy, right? So the sense in which dynamical laws must conserve energy is of course not going to be, say, it's not going to be mathematically necessary or logically necessary. It's going to be necessary in some form that's weaker than those, but that's stronger than mere gnomic necessity. So physical constraint laws are going to have modal force, but they're going to sit in a kind of intermediary modal place, weaker than logical, metaphysical, or mathematical laws, but stronger than mere gnomic necessity possessed by standard dynamical laws. And if the law of conservation of energy is indeed a constraint, it explains certain properties of the dynamical laws. And you have, for instance, the best explanation playing a role here. So why believe that the law of conservation of energy is a constraint? Well, because it's the best explanation of the phenomena we see which will conserve energy. So if you see some kind of, so one of the ways in which we kind of get an epistemic grasp on what the actual constraints are in the world is by looking at, what might be coincidences and then seeing if there's an explanatory constraint that would tell us why all the laws of nature, for example, have a certain kind of property. Okay, so I think that's all a good, interesting picture. Obviously, we need to say more about it, but it seems that seems nice and kind of, and at least clear and plausible, modulo a modal metaphysics. And that's the topic of a big chunk of Lang's book, right? But what I want to do now is drill down into just one very particular little example that he gives relatively briefly, which I actually think sort of solves a kind of debate in philosophy of space-time physics, or solves it, adds a really interesting dimension to a debate in philosophy of space-time physics. So let me take you off into a little bit of philosophy of physics. If you maybe you already thought we were doing philosophy of physics. So here's a debate that anybody who has hung around Oxford in the last 20 years ago sort of cut their teeth on in the philosophy of physics. It's largely been kind of popularized by Harvey Brown. And it started off in a paper by Harvey Brown and Oliver Pooley. They gave an argument against the reality of Minkowski spacetime. That is, an argument against the reality of the spacetime manifold that underpins special relativity. They said, look, rather than so something like the orthodoxy in special relativity is that there's a spacetime with certain kinds of properties, a certain kind of geometry, and it dictates things like time dilation and length contraction, characteristic relativistic phenomena. But Brown and Pooley said, no, look, that's not how we should think about the Minkowski metric. You shouldn't think of it as a spacetime, something substantival that dictates the behavior of the things within spacetime and the laws within spacetime. We should simply think the Minkowski spacetime as encoding of the Minkowski space metric as encoding the Lorentz symmetries of the dynamics rather than explaining them. So effectively, in the context of this kind of Lang language we're using, right, they're saying, look, we must think of the Lorentz symmetries of the dynamic as a coincidence. And the fact that we use a Minkowski metric to describe special relativity just falls out. It's just a way of encoding that coincidence, that brute fact about the world. And they use that as an argument against space-time substantivalism. They say, look, that means that if you're doing special relativity, at least, the Minkowski metric doesn't play the kind of role that would justify reifying it. We can't appeal to the existence of the Minkowski metric via inference to the best explanation, because the best explanation for the phenomena we see isn't the existence of the Minkowski metric. So it's a glorious non-entity, as they put it. Now, you'll already see there's a heavy explanatory flavor to this kind of debate. And Brown and Pooley, and perhaps unhelpfully, kind of push on that explanatory flavor by appealing to this particular kind of distinction that Einstein made. So between principal theories and constructive theories. And Einstein famously said that there were two kinds of theory, roughly speaking, in the world. There were theories like thermodynamics and special relativity that appealed to empirically secure general principles, but weren't explanatory in the same way as some other theories, namely constructive theories like quantum mechanics or the kinetic theory of gases, which offered you a kind of bottom-up causal dynamical account that was grounded in the fundamental constituents of the physical world and therefore offered explanations. This is all kind of grounded in a particular quote from Einstein, and I mean, who knows whether Einstein really thought this. But there's a nice quote from Einstein that kind of makes the distinction. And the thought is when we have only a principal theory, we should look for a constructive theory to better understand phenomena. And so on this view, attributed to Einstein, correctly or incorrectly, special relativity is a principal theory which needs a constructive theory. Then Brown and Pooley claim that the full Lorentz covariant dynamics governing matter is the constructive theory underneath it. And all of the principles of special relativity are doing are encoding the fact that the physical laws that underpin our theories of matter are in fact Lorentz covariant. So that was first developed in a paper by Brown and Pooley and then in a book by Harvey Brown, and garnered quite a lot of attention and quite a lot of counter argument. And that counter argument fell into two camps. There was quite a lot discussing the importance or the precision or the viability or the exegetical accuracy of the principal constructive distinction, which is all very well, but it's not entirely clear that that kind of criticism really met its mark. I mean, after all, there's a way to run this debate where you just talk about inference, the best explanation to Minkowski spacetime. There was a second kind of camp of response to it, which is sort of a more obvious one in a certain sense, that says, look, we already have an acceptable constructive version or explanatory version of special relativity that appeals to Minkowski spacetime. So Einstein writes down this theory in 1905, and in 1908, Minkowski gives it a geometrical formulation. And you might think something like the unwritten orthodoxy of the philosophy of special relativity is the one Minkowski did when he wrote down a geometrical formulation of special relativity, is he gave us a theory that had an explanatory underpinning. You explain all of the phenomena that Einstein talked about by appeal to the geometry of Minkowski spacetime itself. Now, how does that work exactly? Well, the thought is that if you reformulate special relativity in four-dimensional terms, the Minkowski metric just appears directly in the equations. And the three-dimensional dynamics, which is subject to the Lorentz transformations, just emerges as a consequence of this formulation. Of course, that's kind of a mathematical sounding explanation. So there's then this extra step. You have to take the metric to represent spacetime itself. And then explanations that appeal to the Minkowski metric are constructive. And they explain the phenomena based on a basic constituent of reality. So you might think, as long as the Minkowski metric sticks into your fundamental ontology, you're explaining things in just the same way that you're explaining when you give a kind of molecular theory of gases or something like that. But the trouble here is that it's not quite clear what one's doing with the word explains, right? So Brown and Pooley reject that account, and they reject it partly or perhaps wholly on explanatory grounds. Doesn't really matter whether we like the principal constructive language or not, or whether we prefer just to talk about inference, the best explanation. If you want to appeal to the idea that the Minkowskian account is the explanatory version of special relativity, you're depending on the idea space-time structure can explain the behavior of bodies. But no one's got any idea what kind of explanation that is, right? There's some work by Graham Nerlich that kind of tries to pitch it as a kind of causal explanation, but I think Brown and Pooley are rightly really skeptical of that. How an appeal to four-dimensional space-time structure could be causal is really, really opaque. There's just this, there's just space-time with its structure four-dimensionally. And the idea that could be part of, I mean, it can ground counterfactuals of certain kinds, but it doesn't look causal in the kind of classic sense. So to my knowledge, there just isn't in the literature a decent account of spatiotemporal explanation. I think that there are some accounts of mathematical type explanations that look at kind of broadening notions of causal explanation to counterfactual dependence that could apply here, but no one's really done the work on spatiotemporal explanation until Lang, who's not really trying to solve this debate at all. But as I say, big debate in philosophy of physics. And Lang, in just a few pages of his book, decides to consider the explanation of special relativity's Lorentz transformations. So he asks this Brown-Pooley-esque question. Do the Lorentz transformations merely encode the special relativistic symmetries of the dynamical laws, or do they in fact constrain the dynamical laws? Now, obviously, Brown and Pooley are saying that they just encode symmetries of the dynamical laws. There's just this brute fact that all of the dynamical laws are Lorentz covariant. But Lang says, no, look, let's think of that as a constraint. And moreover, Lang believes in a kind of nested hierarchy of constraints. So you explain the fact that the Lorentz transformations constrain the dynamical laws by the fact that the Lorentz transformations themselves are explained by higher constraints, namely the principle of relativity and the invariance of the space-time interval. So this is a direct kind of counter to the Brown-Pooley argument. The idea is that the Lorentz symmetry of the laws is absolutely not a brute fact. It's explained precisely by symmetry principles and by principles of constraint. So according to Lang, the invariance of the space-time interval is a constraining principle of special relativity. That invariant form of the space-time interval just is the Minkowski metric in a really good sense. Once you've developed the theory of the space-time interval, you have given the Minkowski metric. So anytime you appeal to the Minkowski metric, you're basically appealing to an explanation by constraint. So what spatiotemporal explanation is, according to Lang, is explanation by constraint. I think there's something quite nice about this view, because there's something slightly frustrating about the thought that the Minkowski metric doesn't explain at all. I mean, many physicists and many philosophers of physics have found geometrical presentations of relativity hugely explanatory. There is a real sense in which once one kind of gets the geometry, one feels like one's gotten something about relativity. At the same time, there seems to be something in the Brown-Pooley argument that says, look, but nobody can tell me sort of what kind of explanation you think that you've glommed onto there. And I think there's something really nice about kind of bringing those two things together. And I think one nice thing about it is it's not actually a vindication of the orthodox Minkowski substantivalist. So it puts your kind of finger on what was kind of uncomfortable about the contrast you had in this debate in the philosophy of physics. According to Lang, principal theories do explain, and special relativity is a principal theory. So one of the things he's going to do is kind of deny the claim that principal theories are non-explanatory and constructive theories are superior. An inference, the best explanation, is going to justify belief in the invariance of the space-time interval. But even though that's going to encode all of the information in the Minkowski metric, it's not particularly itself an argument for reifying space-time itself. So what we have here is a view that both gives a developed counter-spatiotemporal explanation and kind of gives you a new option in opinion space, something that can do justice to the way that we treat geometry, but equally kind of saves you from substantivalism about the Minkowski metric, which I think lots of people have found particularly unattractive in special relativity, where the geometries are kind of fixed background. Good. So should all philosophers of physics sign up to Lang's views on explanation by constraint? Well, not quite perhaps, because you're going to get a lot of philosophers of physics who are a bit squicky about certain kinds of deep modal metaphysics, and you're going to have to buy quite a lot to buy this whole picture. So what you have to buy Lang's version of this is this nested hierarchical modal metaphysics. So as I noted at the beginning, principles like energy conservation or the relativity principle are meta-laws. They sit in a point in the modal hierarchy above dynamical laws, but below logical, mathematical, or metaphysical laws. So you've got a multi-layered modal structure just to begin with, but it's not like the sort of only those 3 layers, depending on how you count them. You're going to have a lot of modal structure in between dynamical laws and, say, mathematical or logical laws. Different principles or meta-laws possess different modal strengths. And that's why the relativity principle and the invariance of the space-time interval are going to explain the Lorentz transformations, but the Lorentz transformations aren't going to explain the relativity principle and then the invariance of the space-time interval. So all of those things are going to explain what's at the bottom, the symmetries of dynamical laws, which are of course then going to explain physical phenomena themselves. But we're going to get this kind of explanatory hierarchy corresponding to a modal hierarchy. So here's a bad photocopy from, probably a photo taken on my phone, from Lang's book. So apologies for that, it's not terribly legible. But the idea is you have a kind of pyramidical structure of modal facts. So at the top you have broadly logical truths, and then you at the bottom you have dynamical laws, and then you have all kinds of things in between. And the levels of that pyramid are what Lang calls subnomically stable sets, which are basically sets of laws such that taken all together, you can kind of determine and the set below, if that makes sense. I'm not quite getting that quite right, but the idea is that effectively you'll have taken all together, they're kind of closed set that pick out a set of sub-laws, if that makes sense. Okay, so you can definitely write down that kind of hierarchy in a way that looks pretty plausible, in a way that you could get a reasonable number of people to agree with. It's certainly true that for a lot of purposes, physicists are going to treat symmetry laws as sacrosanct, but consider non-Minkowski geometry. So physicists will hold some set of stuff fixed and permute the stuff underneath. But there's kind of opportunism to the way that physicists behave that doesn't quite do justice to that. So one might naturally think, so I mean, in fact, I think Lang puts these at the same level, but it might be natural to think that the principle of relativity is more constraining force than the invariance of the space-time interval. You've got lots of theories like Newtonian dynamics that obeys the relativity principle without a space-time interval or metric. So then you think, okay, well, fine, whether or not Lang says so, the right rule is that the principle of relativity sits at a higher level in your modal structure. But the trouble is you can find examples that push in the other direction too. So you can get alternative gravitational theories that possess a Minkowski metric and hence an invariant Minkowskian interval, but have dynamical laws whose symmetries don't make the relativity principle true in inertial frames defined by that metric. So if you're anywhere in this literature, some of Harvey Brown's favorite examples, teleparallel and bimetric theories, fall into that camp. So physicists don't always behave as if there's a single modal hierarchy. Now, of course, Lang can say so much the worse for some physicists. What he thinks is that, look, at least some physicists, perhaps most, are just in error about the modal hierarchy. But those are standard scientific disputes. They're subject to empirical verification. I take it he thinks that if bimetric theories are falsified or disconfirmed in some way, then we have evidence for the modal status of the relativity principle. If all of these theories end up failing, then we think, look, well, the relativity principle probably is somewhere quite high up in the modal hierarchy. Of course, it's going to be, I mean, I don't know if this is an objection against Lang, it's going to be hard to get empirically at some of these facts, but they're going to be at least, subject to empirical confirmation in the way that kind of deep overarching laws might be. Now, Lang's book has lots of examples like the conservation of energy, in which the practice of physicists does seem to suggest they treat these as empirical matters. But I'm not quite sure that that does justice to the way that physicists behave in general. And this is, I mean, this would need a closer kind of evidence-based case study. But I have spent a little bit of time thinking about these alternative theories like bimetric theories. And if physicists really thought that there was a modal hierarchy that was a matter of empirical confirmation, you'd expect people to be directly arguing against these theories because they contravene certain kinds of constraint laws in the wrong order in the modal hierarchy. It's not that you can't think about things that contravene constraint laws. It's that there's something odd about not formulating your theories in accordance with the actual modal hierarchy. In practice, I think physicists treat modal hierarchy as fixed in certain contexts, but fungible much more generally. And in particular, they seem to treat it as stipulative. They seem to stipulate some set of principles in the context of a particular domain of theorizing that fix the content of sets and the content of theories. Now, they might be wrong to do this. We might think that we should go with the physicists who do fit Lang's examples better. But let's just suppose that there's something in that, and suppose perhaps that we're a little bit squicky about the kind of full metaphysical picture. What might one say? Well, one thing that gets quite tempting, that I'm very tempted to say, is that there is something that's gone wrong in some of these theories that use a Minkowski metric, but without the relativity principle. And one of the things you might think that's gone wrong is that they don't have anything that would really be recognizable as Minkowski spacetime in them. That's because in the absence of the relativity principle, the dynamics aren't going to be constrained in the appropriate way by the Minkowski geometry. So you do need the relativity principle to kind of to get the two things to match. And one thing you might want to question is whether the metric of the theory is really representing space-time at all. So one thing the relativity principle seems to be doing is kind of putting the space-time in Minkowski space-time, if you like. So I think it does, and I mean, this is for reasons totally tangential to explanation by constraint. I'm a fan, as anybody who's heard me talk in the last 10 years will know, I'm a fan of a view called space-time functionalism, which basically says, look, you can come up with all the geometries you like, but you haven't described a space-time unless something plays the space-time role, and the relativity principle turns out to be central to that space-time role. And so on that kind of view, which depends very particularly on a certain kind of functionalism, the relativity principle is modally prior to the invariance of the space-time interval, just because unless the relativity principle holds, the concept of space-time isn't applicable. You can't make sense of the notion of a space-time interval at all. Okay, so you might not all want to be space-time functionalist, but that's one way, which I think is, which I intend to be fairly metaphysically mild, that you might kind of introduce features of this modal hierarchy. And one question is how far-reaching a view like this one can have. So perhaps let's throw the functionalist word out the window, but explore some related concepts and think of modal hierarchy as fixed not by deep metaphysics, not by kind of objective metaphysical facts in the world, but by some kind of stipulation. Now, it's going to be very tempting to think those stipulations are something like constitutive key scientific concepts. And the idea I have in mind here is something like Friedman's constitutive a priori. So the thought is perhaps there's a lot of truth in Lang's explanation by constraint, but the way we should think about the modal hierarchy he's proposing is as fixed by these constitutive a priori concepts that physicists introduce, which is exactly the kind of role Friedman thinks that constraint principles play. They play a role in constituting the terms in other theories, and therefore they become kind of relativized or constitutive a priori for a given theory. And so the question I'm grappling with now that I don't have an answer to is how plausible is that, and how much of Lang's explanation by constraint advantage can we get on a view like that? I'd love to give you the answer, but I haven't quite worked it out. But anyway, topic for discussion. Great, thank you very much.